Hello, I'm here again to continue vector addition problems, practice problems. And I'm wearing a different hat for you guys because all you ever see is me wearing ball caps or not wearing a hat. And I like to mix it up. So this is what I wear when I do my yard work so I don't burn my beautiful complexion. And since I'm inside, it's completely ridiculous. Whatever it takes to keep you guys engaged. So here we go. We're looking at, gosh, I can't take myself serious right now. Okay, we're looking at our second problem, right? Number 2. So we're continuing on the correct pages for this section of practice problems, right? And that is included on the table of contents. Just check that out on the stream. You'll know where to be. We've been doing nothing but displacement vector problems because they're the easiest ones to start with because it's so visual. I mean, if you go this way, then you go this way, then you go this way, right? Then your displacement, your final resultant displacement would be like from here down to here, right? And so it's like, oh yeah, even though I went and did all this stuff, I ended up down here and I started here, so my resultant vector is down to there, right? And it makes a lot of sense. But again, this idea of vector addition works for any type of vector. It doesn't have to be displacement vectors. Let's do a velocity problem. So we got a raft crossing a stream. In this raft, I should have said a boat. This raft has a motor. I know rafts don't usually have motors, but suspend your disbelief. This one does. So a raft crossing a stream has 3 velocity vectors acting on it. Yes, okay. The picture will help us understand this. So we've got, let's draw a stream, kind of like an above view of it, right? A bird's eye view is what I call it. And there's the rocks, right? And there's like some cattails from above. Can't really draw grasses that easy if you're looking from above. There's another rock. Get on with it, Mr. Heinrich. No, you can't make me. I'm going to draw rocks for a little while. No, let's get to it. Okay, we got a raft, and there it is, plain and simple. And it was like log rafts. And we know for a fact that this stream has got a current going one way or the other. So let's make the current going to the right. So we're going to have a current going this way. So I'll say there is a velocity vector this way acting on the raft. V, let's say stream. Yeah, V sub S for V stream. And we'll say it's 5 meters per second. That sounds good to me. There's a 5 meter per second velocity from the stream. And even though I drew the vector over here, you can be sure that it's acting on the raft. Also, the water's passing underneath the raft and trying to pull it in this direction because of the velocity of the stream. We also have a little outboard motor on the back of our boat right here, a little outboard motor. And this motor is giving it a forward velocity. Let's say maybe make it a little bit bigger, maybe like that big. Forward velocity of, and we'll see Vm for V motor. And we'll have some white out. No, oh well, who cares? So I'm going to make this longer, okay? So the velocity from the motor is a much longer vector, and we'll say it's 10 meters per second. Looks good to me. But at the same time, as if things aren't already confusing enough, we have a velocity from the wind. There is a breeze that's blowing, right? And it's blowing kind of like in this axis right here, right? Like that. So we'll say there's a velocity from the wind, V sub W, and let's make it considerable. Now I want to make it a big old velocity. And even though I'm not drawing this on the raft, we know the raft is getting affected by this wind, okay? And this V wind, which I will definitely make that long. Let's see how long that is. I was trying to go 20. Sure, let's go 20. 20 meters per second. Now it kind of looks like it's at 45 degrees, but I don't want to make it that easy. So I'm going to say 55 degrees. Give me a second here. 55 degrees like this. 55 degrees, which would be We are of the north and we're twisting to the east, right? So east of north. Okay, there you go. There's your three vectors that I discussed. And we have to add these together and find out the ultimate velocity that acts on this boat. Because you can imagine if it's getting blown like this, pulled like this from the stream, and propelled like this, that it's not going to just simply go from point A to point B, right? It's not just going to go straight across the stream. In fact, you can kind of see this with me. It's getting pushed to the right quite a bit, so it's probably going to end up somewhere downstream, like over here, right? Somewhere over here when it's all said and done. And that is another problem. We could actually solve for that displacement, but let's not do that. Let's just find the resultant velocity. So I'll say here, find resultant velocity on the raft. Okay. Now I discussed this, kind of figured it out while I was making the problem with you. What do we do again to find our reference angle here, right? Because I drew the vector for you. And a lot of times in these problems, you'll just get this. You'll get the words, and it'll be up to you to draw this vector. So I kind of went backwards this time and actually drew the vectors for you, right? But that's okay. Remember, this idea of east of north, you would go to the tail of the vector, put a little xy axis here, little xy axis, right? And 55 degrees east of north. Who do you belong to? You are of the north. You belong to the north and you swing to the what? The east. You're up, that's an E right there. You're of the north and you swing to the east. This is your 55 degrees right here. So sometimes when we're not doing displacement problems, a lot of times you'll see the vectors kind of just all over the place like this. Now that doesn't mean anything's changed. What is our method for adding these vectors? You should put them head to tail. You should definitely do that. So let's make that picture happen. Do that right down here. And again, this isn't the only technique that works. There's parallelogram method, we talked about that, right? We also could just find the components right here in this picture and then bring those together. But let's stick with the same process so I'm not throwing you too many curveballs while you're still learning how to do this. Now, we already determined that we're of north and we swung to the east. And after we figured that angle out, 55 degrees, we went how far? We have a vector that's how big? 20 meters per second big. Like that, 20 meters per second. So that's the way our velocity is going. We're calling this guy v sub w, and that's 20 meters per second. Now let's take the next vector that makes the most sense to me. I'm going to take this one next. I'm going to take this one, pull him off the page. He's like a little building block, right? I'm going to put him right here. Boom. And we'll call this one vs for 5 meters per second. And then finally, we have 10 meters per second. And it looks like I did kind of a poor job, like I've discussed with you before. You have to be careful of this, right? If I put my 10 meters per second here, I'm going to run into my words. Here is the great news. Great news is right here. You can add vectors in any order you want to. Refer back to the first lesson. I'm going to take this vector. He's a little building block. Boom, take him off the page. I'm going to put him right here because I can. So I'm going to put it right there. That looks good to me. And I'm going to notice I haven't broken any rules. The head of this vector, Vm, that's the velocity of the motor, which is 10 meters per second. His head is touching the tail of the next vector. So this is perfectly fine to do. You could add them in any order and still get to the correct answer as long as you put them head to tail. All right, now let's visualize our answer real quick. It's going to be a bit before we can get to our answer that I'm going to draw, but this is the answer we want to get to at the end of the problem. You start at the tail of the first vector and you work your way right there. to the head of the last vector. This is the ultimate velocity, I'll call it v sub r. The resultant velocity of all three of these velocities acting is something that we need to find, and there it is. How long is that? Well, looks like it could be, I don't know, what, 30? About 30-ish maybe? What angle is it acting at? According to my drawing, it looks kind of like 45. Maybe it's about 45 degrees. Maybe it's about 30 meters per second big, right? I was about to say meters. These are not displacements. These are velocities. So what's our next step? I took a lot of time on the last problem. This one I'm going to go a little bit faster. My next step is to ask myself, are each one of these vectors acting purely in the x or the y-axis? Is this one acting in the y-axis? Yes. Is that one acting in the x-axis? Yes. Is this one acting in the x or y-axis by itself? Meaning, is it? No. It's not acting purely in the y or the x. It's at an angle, and if you have an angled vector, you have to break it into, say it, components. You have to break it into components, correct? Yes, you do. So I'm going to do that. Now, how do you break something into components? You look at the vector you're trying to break into components. You start at its tail. So again, all these other vectors don't exist right now. All we're looking at is this 20. That's all we care about. Start at the tail of 20. And from its tail, you must work your way to the head of that 20 by moving up, down, left, or right. Well, let's move up first. That way we're not running into anything. I'm going to move up. And notice I'm putting an arrowhead. You must put an arrowhead. Moved up, and I'm going to move which way? Right. Right. So that 20 is made up of a bit of north velocity and a bit of east velocity, isn't it? That 20 meters per second is acting both in the north and the east. Up here, I should probably do that. I should say this is, I just thought of this. I should probably state that this is 5 meters per second east and this is 10 meters per second north, right? Okay. Now what? I've got to find these two vectors. I actually have to find the amounts. Remember, if you're struggling with this whole north and east thing, you got to come to tutoring. 1. 2, I'll say one more thing. You could start just by drawing a right triangle, just put in your dotted lines, and then ask yourself, hey, this thing is a combination of what two directions? Up and right. So put an up arrow and a right arrow, please. Okay. Now this side is called what? This side is called VWY. It is the y piece of who? Of who? VW. Remember, this and this are pieces or components of VW. So VWY, and this would be VWX. What is VWY? Well, we have to go to our sine and cosine stuff. So I'm going to remind you over here on the side, the cosine of the angle is equal to adjacent over hypotenuse, and the sine of the angle is equal to opposite over hypotenuse. Just a quick reminder for you. Is this VWY adjacent to 55? Is it touching the 55, this little arc that makes up the 55? Yes, it is. It's right there. They're making contact, right? They're getting close and personal right there. This is the adjacent side. That means what function am I going to use for this adjacent side? The one that deals with adjacent. Cosine theta is the one I'm going to use for the VWY. VWY is adjacent. Cosine 55 equals adjacent, which by the way is VWY. That is the adjacent side, divided by the hypotenuse of 20, right? And I'd multiply both sides by 20. I'd squeeze that in there. Boom, boom. Throw this up for you guys. Let's do a little calculator work. We got 20 times the cosine of 55, 11.47. You know what? That's pretty close to 11.5. I'm just going to call it 11.5 meters per second. Remember, these are all velocities. They're not displacements, okay? VWX, you can clearly see that this side of the triangle right here, this vector of the triangle, VWX, is opposite from 55. So this VWX is opposite. We would write sine of 55 equals the opposite side, which is labeled VWX, all over the hypotenuse of 20. Multiply both sides by 20. Boom, boom. And we have 20 times the sine of 55 is VWX. Let's find out how much VWX is. All right. 16.4. It says 16.38, but I'm going to round it up to 16.4 meters per second. There we go. And I don't want you to get confused. I'm going to put a little divider line here. So let's come back out and see the big picture here. Oh, this is coming together pretty nicely. Do I care anymore about 20? Do I give a hoot and a holler about this 20? No, I don't care about 20 anymore. Please don't cross it out on your paper. You can leave it, but what I'm trying to really emphasize here is that once you find the y and the x of 20, you no longer need the diagonal vector. You have an x piece and a y piece, and we're good. So the only vectors you care about are Vm, Vwy, Vwx, and who? Vs. Don't forget this one. I kind of wrote over them a little bit, but this is Vs at 5 meters per second, right? You got 4 vectors. And now that I see this problem, I kind of wish I had changed some things around. But that's okay. It's still a good problem. It's going to be, I think, a little simpler in a way, which is not bad. We're going to say here now, every vector that we're dealing with is purely in the x or in the y-axis. We are ready to do what? What? We're going to sum up our x's and we're going to sum up our y's. Okay. So I'm going to say sigma, which means to sum up the what? The velocities in the x-axis. Let's sum up our velocities in the x-axis, no problem. Get this, both of my x velocities are heading which direction? East. That means I can just add them both together because they're both going the same direction. I don't have to worry about subtraction. I don't even have to worry about which one's bigger than the other one because they're both going the same way. So it doesn't matter. But if you want to stick with always writing the biggest thing first, that's fine. 16.4 meters per second plus who? 5 meters per second. They're both going east. And you can see that would give us, is that 21.4? I'm pretty sure it is. I just don't want to make any silly mistakes. 21.4 meters per second east. All right, 21.4 meters per second east, cool. And let's check out our y-axis. Let's sum up our vectors. In this case, the vectors are not displacement. I keep saying it. What are they? We're summing up the velocity vectors, the velocity vectors in the y-axis. Would you agree they're both going north? Absolutely, right? 10 meters per second plus who? Plus 11.5. Okay, let's find them. Well, we know that. Whoa, you see what I'm seeing? That's 21.5 meters per second. Now, those who know their geometry pretty well, what's this angle going to be here? It's going to be pretty darn close to what? 45 degrees. How do I know that? Because your x and your y side of the triangle are pretty much the same. They're off by 1/10. And I didn't plan that, it just happened. Okay, it's okay. So let's still go through the process like we don't know that. All right, I didn't know that. Okay, so what would be the next step in any old vector problem? What is the significance of this answer in this answer? These two answers are the x and the y component of your final vector VR. And you can pretty much see I kind of drew that, right? These two brown vectors together. Can you see those two together? Isn't that really just that right there? Oh, forgot to put a north, right? It isn't, aren't these two x vector is pretty much that right there. But just for the sake of drawing a separate picture, which I really want you to do for your own sake, let's draw a separate picture. I'll just continue it down here like this. I would have how much east? I'd have 21.4 east. All right, and I'd have how much north? 21.5. Right. Pretty much the same length, right? So this is 20, looking down my paper, 21.4 east. And this baby is 21.5 north. Yeah. Notice I put them head to tail, right? And the result vector I'm looking for goes from the tail of the first to the head of the last. That is VR. And I think you can agree that that VR is pretty much like that VR, right? They're pretty much identical. If I can get it both on the screen, I can't quite, but you can see what I mean. So redraw your triangle with your sum of the x's and your sum of the y's. This is your 1x, this is your 1y. Together, those two components make up the answer that you're looking for. And it really becomes obvious that this is the A, this is the B, and this is the C for our Pythagorean theorem, right? Pythagorean theorem. So I'm going to say VR is equal to the square root of 21.4 squared plus 21.5 squared. And I should have put units. This is meters per second. That's meters per second. That's okay. Let's find our answer. Square root of 21.4 squared plus 21.5 squared gives me 30.33. We'll say 30.3. That's fine with me. So the answer is 30.3 meters per second. This is 30.3 meters per second. That's how much velocity is kicking in which two bearings? What two bearings are we dealing with? Because we have to get to the direction now. So we found the magnitude, yay, but now we got to find the direction. I want to find this angle. The angle, by the way, is the direction if you haven't caught that yet as we've done these problems. That angle right there is the direction. But again, where am I at? Am I in the south? Am I in the west? No. And how do I know? How do I know that I'm not in the wrong? Let me restate that. How do I know which region of the compass I'm in? You must do this last step correctly. Here's my final vector. There's the head of it, and there's the tail. At the tail of the final vector, please, please, please put a little XY axis. And now you can clearly see that would be north, that would be west, that would be east, that would be south, right? You can clearly see we're in the northeast quadrant, right? The first quadrant. And this is the angle I want to find because it's within the triangle and it makes sense, right? I don't want to find this angle. I mean, you could, but there's really no need to find that angle because those who want the extra bit, listen, if you found this angle up here, this angle is the same as that angle, right? Because that would be an alternate interior angle with that one. But it's kind of extra work for no good reason. Let's just find this one because it's already inside of our triangle, yeah? By doing tangent of theta equals my opposite side, it's always opposite over adjacent, 21.5 over 21.4. Let's take the inverse tangent of both sides. Theta would be the inverse tangent of 21.5 divided by 21.4. And let's actually calculate it. Second tangent of 21.5 divided by 21.4. I'm telling you, it's going to be close to 45 degrees, 45.1. And again, that should make sense to those who know their geometry, right? If you have two sides of a right triangle that are pretty much the same, that means this is a 45, 45, 90. So I'm going to say here at 45.1 degrees, final test of your understanding, the final part. Am I east of north or am I north of east? Pause the video, try. Okay, here we go. my angle arc right here is not touching north. It's not even close to touching north. It's touching who? It's touching the east. I am of east, and which way do we have to swing from the east to get to who? To get to our answer vector. This is our answer. That's all we care about, right? That dotted vector. Which way did I have to swing from the east? I had to swing north, didn't I? Didn't I have to swing towards the north? I am north. This dotted vector is 30.3 meters per second at 45.1 degrees north of my east bearing. There's your answer. So if you're looking back at your raft and you're trying to make sense of the physical situation, which is what physics is all about, by the way, using math to make sense of our physical world around us, you can see that this raft is probably going to end up right about there because it's moving at a 45-degree angle, just like that. So when it gets to the other side, it lands a little further down the shoreline, but that's okay, right? Well, I hope it's okay. I hope that there's, you know, not a bunch of treacherous rocks or man-eating piranhas or something right over there. Anyway, enough silliness, enough foolishness. Have a great day. We got one more practice problem to do. That'll be on another video. See ya.